Welcome to Consumer Times. Today, we're diving into an essential yet often overlooked aspect of precision engineering: measurement uncertainty in dimensional measurement. If you are involved in manufacturing, quality control, or metrology, understanding measurement uncertainty is critical for ensuring accuracy, compliance, and confidence in your measurements. We'll cover what measurement uncertainty is, why it matters, how it's evaluated, and some practical insights for reducing uncertainty in dimensional measurements. So, let's get started. Before we get started, please comment, like, share, and do not forget to subscribe our channel to motivate us. The measurement uncertainty refers to the doubt that exists about the result of any measurement. No measurement is perfect. There is always some level of error or variation due to different factors, such as instrument limitations, environmental conditions, and operator influence. In dimensional measurement, uncertainty is crucial because manufacturers and quality inspectors must ensure that parts and components meet design specifications with high precision. A lack of awareness of measurement uncertainty can lead to incorrect decisions about product conformity, causing rework, rejection, or even safety risks. The measurement uncertainty matter due to accuracy and reliability. Understanding uncertainty ensures that dimensional measurements are dependable. Regulatory compliance. Many industries, such as aerospace, automotive, and healthcare, require uncertainty analysis for compliance with standards like ISO 17025. Decision-making helps in determining whether a product meets specifications or requires corrective action. Cost efficiency. Reducing uncertainty minimizes errors, rework, and wastage, saving time and resources. By properly evaluating uncertainty, organizations can ensure that their measurements are both accurate and traceable. Factors contributing to measurement uncertainty. Several factors contribute to uncertainty in dimensional measurement. Instrument limitations. No measuring instrument is perfect. Factors like resolution, calibration errors, and wear and tear affect accuracy. Environmental conditions. Temperature fluctuations, humidity, and vibrations can impact measurement results. Operator influence. Variability in human handling, such as differences in applied force or reading interpretation, can introduce uncertainty. Material properties. Some materials expand or contract due to temperature changes, affecting dimensions. Measurement methodology. The procedure and techniques used also influence the results. Poor setup or misalignment can introduce errors. Understanding these factors helps in selecting the right tools, techniques, and calibration methods to minimize uncertainty. Evaluating measurement uncertainty. Measurement uncertainty evaluation is a structured process that follows guidelines such as ISO, IEC Guide 983, GUM. It involves several key steps. Identifying sources of uncertainty. List all potential sources of uncertainty, such as instrument precision, environmental conditions, and operator influence. Quantifying uncertainty components. Each uncertainty source should be quantified using data from calibration certificates, past measurement records, statistical analysis, manufacturer specifications. 3. Classifying uncertainty types. Type A uncertainty, based on statistical analysis of repeated measurements. Type B uncertainty, based on manufacturer specifications, experience, or reference data. 4. Calculating combined uncertainty. Once all individual uncertainties are identified, they are combined using the root sum square (RSS) method, where U_C is the combined uncertainty, and U1, U2, UN are individual uncertainty components. 5. Determining expanded uncertainty. To account for confidence levels, the combined uncertainty is multiplied by a coverage factor, K, usually 2 for a 95% confidence level. This expanded uncertainty provides a realistic range within which the true measurement value lies. Practical steps to minimize measurement uncertainty. To improve the accuracy of dimensional measurements, consider these practical steps. Use high-precision instruments. Invest in quality measuring tools that suit the required precision level. Calibrate regularly. Ensure all instruments are regularly calibrated against certified standards. Control environmental factors. Maintain a stable environment with controlled temperature and humidity. Standardize measurement procedures. Follow documented, repeatable methods to reduce variability. Train personnel. Ensure operators are well trained in proper measurement techniques and error mitigation. Use statistical methods. Apply statistical tools such as control charts to monitor and analyze measurement data. Real-world example. Let's take an example of measuring the diameter of a machined part using a micrometer. The micrometer has a resolution of 0.001 millimeters. Environmental conditions cause slight variations of plus or minus 0.002 millimeters. Operator influence adds an estimated uncertainty of plus or minus 0.001 millimeters. Using the RSS method, expanding for a 95% confidence level, K equals 2. So, the final measurement should be reported as measured diameter equals 10.000 millimeters plus or minus 0.0049 millimeters at 95% confidence level. This ensures transparency in measurement accuracy and helps in decision making. Measurement uncertainty is an integral part of dimensional measurement that ensures accuracy, reliability, and compliance. By understanding its sources, evaluating uncertainty effectively, and taking steps to minimize it, industries can enhance their measurement practices and improve product quality. If you found this video helpful, don't forget to like, subscribe, and hit the notification bell for more insightful content from Consumer Times. Have any questions? Drop them in the comments below, and we'll be happy to answer. Thanks for watching, and see you in the next video.